Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at AP Precalculus Unit 2. And if you're thinking, well, hey, what happened to Unit 1? We did the Unit 1 a few weeks ago, and you can catch that webinar on our website on demand, as well as any of our other pre-recorded webinars. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. With us tonight, we have two experts, Gail Burrell and Tom Dick. Both Gail and Tom work for TI as senior math advisors, and their backgrounds are extremely extensive. Everything from NCTM president. I believe, Tom, you're in the Oregon Hall of Fame. I'm not sure if it's for football or for math teachers, but still, nonetheless, congratulations on that. But all joking aside, very, very, very distinct backgrounds, and with these two that are joining us tonight. So, Gail, thanks so much for joining us.
Glad to be here. Thanks for having us, Mike.
Yeah. Thank you, Mike.
Tom, same thing. Thanks for joining us. Tom, would you mind talking through our agenda? It looks pretty lengthy.
Okay. Yeah, we're a little ambitious, but we hope we're able to cover most of this. This is part of a series of webinars around the new AP Precalculus course, which is up and running this year. And so we're going to be focusing on Unit 2, its content and the math practices, and really some ideas that might be new to some teachers, even those who have taught Precalculus for a long time, if they're venturing into teaching AP Precalculus. We'll take a look at comparing linear and exponential functions, a connection to arithmetic and geometric sequences. Then we'll take a close look at logarithms, what they are, why they're useful, some properties of logarithmic and exponential functions, and then relate that into regression and modeling and look at how logarithmic and exponential regression compare to linear regression, as well as what are the instances or the contexts where you might expect to see exponential or logarithmic regression models be useful. And then I think we'll then turn it back over to Mike, and he can say a bit more about the webinar drawing later.
Sounds great, Tom. Thank you. And Gail, can you discuss some expected outcomes for tonight?
So I think Tom pretty much covered the content, so the outcomes aren't a surprise. We're thinking about arithmetic and geometric sequences and the characteristics. We're looking at a rate of change for both linear and exponential models. We're thinking about logarithms, logarithmic and exponential regression. And we're going to think about how do we know whether we have a model that's a valid model for our data.
Thanks so much, Gail. As many of you have already noticed, we're going to be using that chat window tonight to send general messages. But also, if you have any questions for Tom or Gail, feel free to use that Q&A window on the right side of your screen. And if it's easier, you can also use the chat window tonight to send those questions. We'll do our best to get those questions answered live. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. All right, Tom, feel free to share your screen. It's all yours.
Okay, I'll be driving the PowerPoint tonight, but Gail and I will be tag teaming in terms of leading the presentation and discussion. So let me get my screen shared. And I think it may come up. There we go. So there's the TI-Nspire, but let me go to our PowerPoint. And I'll turn it over to Gail to talk about the math practices and the content of Unit 2.
Okay, so as you guys, can you go back one slide, I think? Oh, no, good. I'm sorry. Go back to the, I thought there was something missing. Okay, so the, as you might know, the CED, course and exam description, has two large content components to it. One is these three practices, which they call skills, which are really important in the way the ideas that are contained in the content part are carried out. And I especially want to call out two of them. I want to call out symbolic fluency, which it's really important in pre-calculus to start developing kids' comfort with symbols, just because so much of calculus is actually dependent on the ability to navigate around different symbolic representations. And I also want to call out the communication, which is where a lot of students fall apart when they have to explain something. And so that's a really important part that sometimes we in math class don't actually emphasize as much. The second, next slide, please, Tom. The second part of that are the content expectations. The first unit had to do with polynomials. This unit has to do with exponential and logarithmic functions. Next slide, please. And the content there is pretty much what you would expect. So there are some new things, and we're going to be talking about some of these. The idea of validating a model when you're looking at a set of data. How do I validate a model? That's new, I think, for many of you. There's a huge connection between what we're doing with exponents and logs and transformations, and we'll talk a little bit about that. The use of limit notation is introduced. The idea of an exponential model, I'm thinking about whether it's appropriate and what scaling does. There's also some different vocabulary. We're not going to spend a lot of time on it, but those are things you might want to check out on your own. Next slide, please. So tonight, basically, we're going to focus mostly, as we said, on exponential and logarithmic functions and on the idea of modeling, what the transformations that are involved, and scaling for logarithms. Next slide, Tom.
Okay, I'll take it from here. So as you're making that transition from the unit 1, which is on polynomial and rational functions, into the unit 2, where the exponential and logarithmic functions, with the exponential models, I think it's really important and useful for students to make a real direct comparison to linear models, because there's a kind of a striking similarity between the two. So a linear model, which I've written in a form that might look a little bit different to a lot of you, this is the kind of statistical form of the linear, y equals a plus bx. We're used to the mx plus b. But a way to think of the linear model is there's two parameters. One of them has to do with the initial value. In other words, what's the value when x equals 0? Okay, that's the a, where the y-intercept is how we might think of it graphically. And then there's the slope, but that's also, we can think of that as the growth rate.
Tom, remember to use your teacher voice.
Okay. So the growth rate here is, we can think of it as being additive. That means that for every increase of 1 unit in x, that's going to result in an increase of b units in y. Okay. So we know that's kind of old hat to students, but exponential models, we can think in a very similar way. We've got two parameters. Again, I've labeled them a and b. This time a is the coefficient, and then b is the base for the exponential. Notice that when x is 0, the initial value is again a, but now the growth rate is a relative growth rate or a multiplicative growth rate, and that's controlled by that parameter b. So now for every increase of 1 unit in x, the y value will be multiplied by b. So it's really a comparison between an absolute growth rate in the linear model and a relative growth rate in the exponential model. Now, there's a very nice connection you can make. This is exactly the difference between an arithmetic and a geometric sequence. Arithmetic sequences relate to the linear model. We have an initial term, a, And then each term in the sequence, we have this constant add-in of b. So the next term is a plus b, then a plus b plus b, so that's a plus 2b, a plus 3b, and so on. For geometric sequences, we start out with an initial term of a, but now we have a constant multiplying factor. So a, ab squared, ab cubed, and so on. So the arithmetic and geometric sequences relate directly to our linear and exponential models.
Can I interrupt just one little minute?
Absolutely.
I just want to point out, I noted when I talked about symbolic fluency, one of the things that students have a lot of trouble with are subscripts. So might pay attention to the subscripts that Tom's using here.
Okay. So kind of sticking with that emphasis on the additive versus multiplicative, here's an observation. If you take something that will be important in pre-calculus is for students to become skilled at combining functions, either using arithmetic, like addition, subtraction, multiplication, division, or composition. Notice that the linear functions, which are based on this kind of additive model, if you take any two linear functions and add them, you'll get a new linear function. The exponential functions work very similarly, but with multiplication. If you take any two exponential functions and multiply them together, you'll get another exponential function. So here's a question for you to think about. How about composition? What happens when you compose two linear functions with each other? How about two exponential functions? How about composing a linear function and an exponential function? Keep in mind that when you do composition, unlike addition or multiplication, it's not commutative necessarily. So it might matter which order you compose those two in. So would you get some kind of hybrid function, or would you get a function that falls into one of these types? I'm going to leave that as an open question. It's a great one for you to explore and think about. All right, I'm going to turn this back over to Gail, and she's going to start looking at some data.
All right. These are the predicted wildfire risk and the number of acres burned by state throughout the United States in 2021. I'm not sure how well you can see all of these data, but is there anything that you notice or wonder about these data? You feel free to type it in the chat. Anybody notice anything? Looking hard? I'm using my teacher wait time.
They're hoping it's a rhetorical question, Gail.
Is the 0 for Rhode Island? Rhode Island. Yes. Rhode Island did not have any acres burned in 2021. The percentage of states that had burning. All right. Oh, they were looking at Delaware, which has 0. Okay. Wisconsin seems to be relatively empty. Yes, it does. All right. But that's for the risk. Yes.
How recent is this data? I was looking at Hawaii.
2021.
Oh, okay. So
Right. So that's one of the things that I'd be very curious, and I will do, is look at to see what's going to happen when we try to put in the fires that we've had this last year. Okay, and Hawaii is blank because often they don't collect the same data in Hawaii and Alaska that they do in some of the other states. So let's just look at this next question, Tom. So we're going to actually concentrate just on the number of acres burned. And I'm going to just pose the question, Is there a relation between the number of acres burned and the particular regions of the United States? In other words, is any one region of the United States more susceptible to wildfires than the other regions? Next slide. And in order to do this, I'm going to actually tell you about what I do with my students. If we were in person, you would actually be doing this yourselves. So when the kids come into the room, there's a number line that's either drawn on the board, or if I have to, I do it on the floor. I can even do it in the hallway outside. And the number line is marked off in this set of scales in some way to go from 0 to 2,400,000. Every kid is given the data that you just were looking at. They're assigned a state, and they get a sticky note that corresponds to their state. So we've got all these kids. And if I don't have enough kids, like sometimes when I do this in college, I've only got about 18 students, and that's not enough to cover all 50 states. So kids get a couple of states. Next slide, please. And I asked them to post their sticky note, write the number of forest acres burned in the forest fires on their sticky note and post them on this number line. And what do you think happens? Stephen has asked a really good question about scaling for the size of the state. We can maybe come back to that at the end, but what do you think happens here? I don't know if you looked at the data close enough, but things are globbing together. That's exactly what happens. Next slide, please. Oh, no, go back up. Sorry, Tom. Go back, quickly back. All right. Yes, you will be able to get a copy of the data set. I'll make sure that Mike has it. Okay, so no, go back to the next one.
Okay.
There. So how can we solve this problem? The kids are all at the same space, trying to put their sticky notes on this number line. How can I solve this problem? What can I do? Anybody got an idea? Oh, well, now Brandy. Oh, and Rebecca. But you guys, my students have never heard of a logarithm. My students don't know what logarithms are. This is before we've even talked about that in pre-calc. So they need to think of another way to address the problem. I will tell you that one of the first things is to just erase all the numbers that aren't being used. So just have a big gap in your number line. And you guys are coming up with some really good, call them up with groups. So that's an interesting one, but they'd still all be, their numbers would all be piled up. So eventually when the kids are thinking about scaling, they're thinking about it. I keep waiting and pushing, and you have to have a little teacher patience here. You're like, okay, you guys, I can't lose my data. I want to get all those little sticky notes up there. I want every state represented. How am I going to do this? How can I do this? It's got something to do with scaling. And eventually somebody will say, let's write them in scientific notation. Let's use exponents. Next slide, please. And lo and behold, I rush out and I wipe out all my old little scaling, and I put a new scaling up with a new little set of markers, that 10 to the 0, 10 to the first, 10 to the second. And I say, okay, now put your sticky notes up. And the kids are spread out. They can put their sticky notes up. Next slide, please. And I can go back and think about, there's still a cluster, there's still a big group in the middle, but it's not quite as bad as it was before. And I can actually answer my question if that was my purpose. Really though, the purpose that I had in doing this activity was not so much to have my students look and see where the areas were, although you can see like the Northeast does not have a lot of acres burned, at least in 2021. And you can see that the purple ones, which are the Southwest, are pretty high up on the number of acres that are burned. Next slide, please, Tom. But the big deal was the kids should take away from this that the scale is in exponents or logarithms. And this is where I say, okay, you guys, when I write my scale this way, just using exponents, and in this case, it was exponents on 10, I call that a logarithmic scale. And when I write these, I call them logarithms. Next scale. Next scale, next slide. So here's a graph of what the data look like. I did it on an Nspire. You could do it on an 84. And on the left, you see the number of acres burned. You see that one big outlier that's making it really difficult, but it's still hard to do all the spacing. And on the right, you see the distribution. They're not colored anymore, but you can see that the horizontal axis is in exponents. These are exponents on 10. And it's important for students to understand what a dot in that log plot represents. It's the power you would put on 10 in order to get that number of acres burned. Next slide. And the interesting thing, and the question that usually comes up is, well, why did I use base 10? Could I use another base? Like base 2 is really common for those of you that do anything in computers. Okay, so I could use any base. So this one underneath is base 10. To the right, the two slides to the right, one is an ln, natural log, and one of them is base 2. And the awesome thing here, which my kids go, really? The awesome thing is that the distributions themselves look the same. But notice that the scales are very, very different. But if I were to describe the distributions when they're in logs, they would be exactly the same. Next slide, please. So there's some things to think about that I've come across when my students are doing this. They kind of get mixed up on what the scaling is, and they keep thinking halfway is just like halfway between 0 and 100 is 50. They want to apply that rubric when they're looking at this log scale, and that kind of a thinking doesn't work. So questions like these are really good questions to get them to think about. Next slide. And here's some kind of awesome things. I mean, my students were like pretty surprised to note that 10 to the half power is 3.16228. And look, 10 to the 1.5 is 31. How come do you think that is true? Oh, it's 10 to the first times 10 to the 0.5. So there's all these kinds of questions that you can actually talk with students about what's going on when you're working with powers, exponents, logarithms. Next slide, please, Tom. And these next couple of slides are just to show you that things that I always look for when I can find things in the real world that match what I'm doing in my math class. And so Gapminder, I don't know if you've heard Gapminder, but you can just Google Gapminder. And this is a graph of life expectancy versus income. And it starts in 1800 and it goes to 2022. But next slide, please. The cool thing about this is that all of the data, and there's lots of data on this site, all of the data shows that both in a logarithmic scale and in a linear scale. And so you can actually have kids think about, well, what did the linear scale look like and how did that change when you did the logarithmic scale? You can kind of see it straightened out, actually. Next slide, please. And another example, I just discovered this at the end of the pandemic. This one's a little harder to read, but it's the people infected by each sick person with a disease. So if you can see in the right side there, there's measles. So measles is very contagious. So on average, it affects, if you have measles, you're going to infect 15 other people. But it's not very fatal. Very few people die. It's less than 0.1%. or a little over 0.1% of the people die from measles. However, Ebola or bird flu is highly contagious. If you get it, it's not highly contagious. You're only going to infect 1 or 2 other people, but it's very, very deadly. So obviously the point here is if you get one of those diseases, you're not around long enough to infect anybody else. But it's a logarithm scale again. Notice it goes from 0 to 100, and it goes 0.1, 10, 1, 10, 100. And that's because you couldn't get those numbers on that scale and that picture, and they rescaled it so that you could see everything. Next slide, please, Tom. All right.
So why do we look at logarithms? We've already given, and Gail's given some wonderful examples. I mean, historically, logarithms were invented to enable for easier calculations by turning the problem into one of exponents that transforms
Teacher voice.
multiplication, division, and exponentiation problems or calculations become addition, subtraction, and multiplication problems. And those of us who are old enough can remember the days that the school curriculum actually involved working with tables of logarithms. Now with calculators that have a logarithm key, we're able to access those calculations much easier. Gail has really made a case here for how logarithms can be used effectively to rescale data, and especially when the data has some large extremes. I would call attention that some folks in the chat made reference to semi-log plots. And semi-log, we think of semi being half, means one of the two axes is scaled according to logarithmic scale, meaning that it's really picking off the exponent. It's interesting to me, I think that Yale had examples of semi-log plots essentially of two types. One in which the horizontal axis was that was scaled logarithmically. The very last example she showed with the diseases, it was the vertical axis that was scaled according to logarithms. So either axis, it might be useful to have scaled in that way. We're going to see how, in some of the graphs she showed, you could see how using the logarithmic scale kind of straightened out the data. And that becomes really useful in considering logarithmic or exponential regression. And of course, the logarithmic function provides an inverse for the exponential function. In terms of the straightening out of data, here's an example that we found useful. This is in some sense almost deterministic, but it really illustrates what happens when you use a logarithmic scale or for a semi-log plot, if you think. So this would be the number of ancestors one has at each generation. And of course, this goes up by powers of 2. And so you can see how quickly we get that characteristic exponential looking curve. It literally is y equals 2 to the x. But if we employ a logarithmic scale on the vertical axis, so now the numbers 3, 6, and 9 that you see on the left, on the vertical axis in the right-hand picture, right-hand screen, those are now powers of, let's see, is it 10? Is that what we've got here? Maybe you can help me, Gail.
I don't remember.
Or we could check it out. Let's see, what's 2? Looks like we're seeing some, I think it might be base 2, I'm guessing.
But we could try it. Your students should try base ln, base 2, base 10, and see what's different.
Logarithm is being used here.
Yeah.
What's the base on? Well, these are exponents of some base. What base are they? What base is it? Interestingly, whatever base you use, it will straighten it out. It'll just have a different slope depending on the base that you use. So we'll mention logarithmic functions or inverses of exponential functions. I've always preached to my student that any logarithmic equation, they can just immediately write down an equivalent exponential equation that's relating the same information. So the statement y equals log base a of x is exactly equivalent to x is equal to a raised to the y power. It's worth calling attention that that it doesn't make sense to have a being 0 or a being negative. And also, it would not make sense for a to be exactly equal to 1. And I'll actually leave that hanging, let you think about why that wouldn't make sense. And it has to do with invertibility. So calculating a logarithmic value really is, in a sense, meaning find the exponent. What is the exponent? So log base 2 of 8, we'd be asking what power of 2 is equal to 8?
Tom, what is invertibility?
Invertibility would be the function has an inverse. Okay, so that it's when you we think of it graphically, when we reflect it over the line y equal x, the graph, we'll get another function graph. Okay.
Thank you.
And if you think about the 1 raised to a power, it's when we try to flip that, think about what kind of graph you're getting then. Okay. Here's some assessment questions that these were drawn from the Algebra and Precalculus Concept Readiness test from 2013. But I think these are probably good examples of kinds of questions that might be present on the AP Precalculus exam. So assume that y equals log base 2 of 8x for each positive real number x. Which of the following is true? And notice these are asking, okay, as x changes in a certain way, how will the y value change? A big theme in the pre-calculus course overall is the notion of covariation. That meaning a relationship between two variables. How does one variable change when you change the other variable? So that kind of language is something that may be new in terms of an emphasis in pre-calculus. But it's really setting the stage for calculus understanding. This question we just posed is a multiple choice question. It's a fantastic one to explore graphically. So here we ask what happens if we doubled the value of x. And so what we have here is a graph of the log base 2 of 8x. And then the log base 2 of 16x. What would have happened if x had been doubled? And amazingly, looks like these are, could that possibly be right? Is there, let's take a look. It looks like the one graph is exactly one shifted up one vertically from the other graph. What is that related to? I'll let you ponder that, or Gail may want to say something.
Loud. They can't hear you again.
Oh, okay. I'll increase my volume. Okay, sorry about that. But so is that true that the log base 2 of 8x is exactly 1 less than the log base 2 of 16x for all x? Interesting. There's a property of logarithms that's really apparent here. Okay. In fact, here's an observation. Might be surprising. Did you know that any two logarithmic functions, doesn't matter what base they are simply constant multiples of each other? Let's check that out graphically. I'm going to take this occasion to move to the 84 so that we can illustrate this. Okay, let me go to y equals here. And I'm going to do the following. I'm just going to graph a couple of logarithm functions of different bases. Let me clear out my y1 and y2. For y1, let me just use ones that are very handy. There's the common log. So let me go ahead and use that. Common log is referring to base 10. Okay, so there's common log of x. And now let me look at the natural log. That's going to be the log base e. And let's go ahead and graph those. I'll go ahead and do it in a Zoom decimal window. Okay. All right, so there's those two logarithm functions. They both have a shape that's, in the language account, concave down. They both go through the point 1, 0. Are these really multiples of each other? Well, a way to check that out very easily would be to graph a third function that is the ratio between the two. So I'm going to graph the ratio of y2 to y1. So there's y2, we'll divide by y1. And let's take a look at the graph of the ratio. So this is the ratio of the natural logarithm divided by the common logarithm. What kind of function does that look like? My gosh, it looks like a horizontal line. Let's wait a second. I see a hole in it. Where's that hole at? Actually, let me do a trace here. Well, logarithms are not defined for x equals 0. Let me go ahead and trace that ratio function. The ratio is, oh, that's kind of a weird value, 2.302 and change. Let's see. Let me trace over to x equal 1. Oh, it's definitely undefined there. And if we think about it, oh, both of our functions are equal to 0 at x equal 1. So we're getting something that's undefined.
And this is one of the places where the Nspire doesn't compare to what the 84 can do, showing the holes.
That's right. Yeah, it's much easier to see the hole on the 84, actually. Now, what is this value that we found here? And that is the ratio. Let me get over. Okay, so it looks like it's a constant 2.3025851. I'll tell you what, I'm going to change my window slightly. Actually, let me just do a zoom standard. And my main reason for doing that is I was looking for where does the constant graph cross these graphs? And it looks like it crosses right at x equals 10. It crosses my red graph. My red graph, let's see, let's do the trace again. Okay. The red graph was the log base natural log, right? So if I go to the value 10, in fact, I think I can just enter 10. I think that might be exactly where the two graphs cross. So let me take a look at, let's see. Oh, the red graph is actually the common log. Is that right? Or is that, I forget which one. Let me cycle through. Let's see. The red one was natural log. Oh, look, it has exactly the same value. So the natural log of 10 is that constant multiple. So that means that the natural log of x is equal to the natural log of 10 times the common log of x. So there's a relationship between logarithms of different bases. In fact, all the logarithms are simply multiples of each other.
So some folks said, could we use the intersect button command to find that?
Nice suggestion. So let's take a look at that. Let me move a little bit back. And if I did a calculation, that's the shift of trace. I want to calculate an intersect. first curve. Let's do the ratio curve. Second curve, let's do the natural logarithm curve. And we're close enough for a guess. And yes, indeed, that's exactly where the intersection is at the natural log of 10. Okay, let me get back to PowerPoint. And that observation, here's a couple of others that are actually called out in the course description. So I want to call your attention to these because these are fantastic things to do with graphical investigations on the graphing calculator. So a horizontal shift of a graph of an exponential function is going to be equivalent to a vertical dilation of that same function. And because logarithms are inverses of exponentials, notice that that transforms to vertical shifts. The graphs of logarithmic functions are going to be equivalent to horizontal dilations of logarithmic functions. And as I said, these are fantastic opportunities to see these in play graphically. So I think these graphical illustrations of these properties is very powerful. A lot of these properties are ones that we just have a tendency to rote memorize, things like the logarithm of the product is the sum of the logarithms. You can really see those come alive if you use the visualization afforded you by the graphing calculator. There's a couple of other possible assessment questions. And think of how would you want your students to begin thinking about questions like these? Suppose that A is equal to the log of B. And if you change B from X to X squared, how would A change? And here's some different options to think about. This is another example that comes from that algebra and pre-calculus concept readiness test. Here's another one. Which of the following defines the inverse function f, or f of t equals the natural log of t plus 2? And again, this is one that's be very nice to check out once thinking using the graphing calculator. Not going through an analysis of these, but posing questions that we think are ones that are getting at some of the emphases on thinking of logarithm and exponential function families, how they relate to each other. Okay, I think that's it for me for now, and I'm going to turn it back to Gail.
All right. So Halloween is coming. And so some of you may know Rachel Gorsuch. She's a T-Cubed instructor. And she shared this at a summit that we had. She was teaching in a school where it was possible for her upperclassmen to work with some of the kids in the elementary school. And so they went out and they got pumpkins and they collected all this data on pumpkins, and the upper level students helped the elementary students figure out how they might measure things, how they might, what would I do to get the radius? How could I measure the circumference? And the kids had a great time and they got this wonderful data. Next slide, please, Tom. And I'll send a TNS file to Mike so that you can have these data if you want. So to me, this would be a great thing for you guys to do because Halloween is coming up and pumpkins are everywhere. The question that we want to know, I looked at the height and the weight, just kind of arbitrarily, I looked at those two. So we want to know if there's a relationship. So I plopped a scatter plot and I looked at a regression line. And at some place you might want to talk about what a regression really is. But we'll come back to that in a minute. I did put in here this little statement about y equals mx plus b or y equals a plus bx. So some of you might have never noticed or wondered, why both of those are in your 84 and your Nspire option on linear regression. And that's because in the beginning, the very first ones, the statisticians that were working with TI told TI that regression is always done y equals a plus bx. And they put that on their very first calculator. And the teachers had a fit because they wanted it to, they said, you can't possibly have B represent the slope. The slope is always represented by M. So from that day to now, all of the Nspires and 84s have both of those linear regressions. There's no difference. They're just the order. But the question we really want to look at here, next slide, please, Tom, is that a pretty good model? And it actually doesn't look too bad, except the way you're supposed to think about models, if you've got a good model to fit, is to look at the residual plot. The residuals, as you can see in that picture on the right with the little red arrow, the residuals are the difference between your predicted y and your observed y. So there's a y that's predicted by the line, and then there's the y that's a part of your data. And the residual is that difference, that vertical little segment in there. And the idea is that the least squares regression line minimizes the squares of those summed residuals. I don't think you can do this on the 84, but the Nspire has a really nice picture of those squares that you're minimized by using the regression line. The problem here, if you look at the residual plot on the left, is you have a good model. One of the ways to tell is if your residuals do not have a pattern. If there's any prediction that you can do about what your residuals would look like, and what your estimate or your prediction would look like, from looking at the residuals, you've got the wrong model. And this one is pretty subtle, but there's a clear fanning. In other words, the farther you get in the height, the taller the pumpkin, the bigger the variability in the weight. And those of you that know about pumpkins, you can think about that as probably logical, because some of them are tall and they're just like, you know, tall and slender like cylinders, and some of them are tall but fat. So there's a big variability there. So when you can make that statement about some relationship, you can say, and how I'm predicting, it's not a good model. So let's go to the next slide. So yes, what do? We take the logs and we look at the log transformation to see if we can't reduce that predictability in our error or our residuals. And you can actually see, I picked out of the taking the logs, I looked at this and I'm thinking that taking the log of the weight actually gives me the best scatter plot, where I can see the least amount of pattern in the way the residuals are behaving. And here's a really nice space for kids to actually understand what they've got. What I have here, if I were to write the equation of the regression line, not using y equals x, but using my variable names, I have the ln of the weight, because that's what the y value is on the axis, is equal to 0.19 times the height. And you want to have conversations about what that 0.19 means and all that kind of like stuff. But then you have to, in order to get an expression between weight and height, you have to use that transformation to go from the world of logs to the world of exponents. And that, by using the definition and then some of the log rules, now you get a nice clean statement about what, how to express the weight in terms of the height. Next slide, please. This is also a good question. So you could actually look at the radius and the circumference. And here, those of you that really know what we're doing here, and some kids might not, but know that radius and circumference should have a really pretty good relationship, because circumference of a circle, which is what they're going to probably measure, is 2 pi r. So we should, next slide, please. We shouldn't be surprised if we put in a linear regression and we can see that there's no pattern in the residuals. They're pretty randomly scattered. Next slide, please. So you can do the calculations, the statistical calculations. Some of you probably already know this, but on both the calculator or notes page, or you can do it on a spreadsheet page. This is in the Nspire. There's several ways to get these calculations on the 84 as well. One of the things that pops up when you do these calculations is that R. See that little red arrow? And it says the R, which is correlation, is 0.952903. Next slide, please. So that is pretty awesome. But the really big deal is correlation does not tell you how well a line fits the data. Correlation only tells the strength of a linear relationship and the direction. Correlation is not in the CED for precalculus, but this idea keeps coming up, and it's one that we want to make sure is not misunderstood. So here are several resources, both on the 84 and on the Nspire, that you can go to explore to get a better understanding of what correlation really is. Next slide, please.
Okay. So one of the options when you have data on the TI-84 or the TI-Nspire is that you can perform, besides a linear regression, you can actually choose to do an exponential regression or a logarithmic regression. So exactly what's going on with those? Well, intuitively, it's about fitting an exponential curve. That means the graph of an exponential function to data, which is we visualize as a scatter plot of XY points. So how do we decide which exponential curve fits best? Well, similar to linear regression, we could look for the exponential curve whose y values minimize the sum of those squared differences with the data y values. In other words, the sum of the squared residuals for each corresponding data x value. That's just saying, okay, which of the exponential curves satisfy that least squares property? There are some software packages that literally do that. They find an exponential curve that minimizes this least squares. It finds the least squared residuals. However, many packages, including the TI calculators like the TI-84, actually do a different approach. And in fact, they do an approach that's quite similar to what Gail just illustrated. Let's just kind of go through that so you have some understanding of it. So when you employ like an exponential regression on the TI-84, what it's doing actually is it's first transforming your y data by taking the logarithm. Any base would be okay. So just for illustration, let's suppose the calculator used common logs. So for each y value, it would take the log base 10 of that y value. Then that new data, so we'll take our original x data that's now paired up with the logarithmic data. Let's do a linear regression on that data. And so we'll get a function of the form w equals cx plus d. And now with that linear function, let's take the 10 to the power of each side of that equation. Now, when I take 10 to the w, I'm back to my original y. But notice when I take 10 to the cx plus d using properties of exponents, I'm going to get a 10 to the d, which is some constant, times 10 to the c, which is in turn raised to the x. Well, if I call 10 to the d a and 10 to the c b, that's exactly the form of my exponential formula. And so now that's how exponential regression is done. You might ask, does that give you exactly the same thing as fitting an exponential curve directly to the data? Well, you might be surprised. The answer is no. It's actually a little bit different. It does give you a pretty good fitting curve, but it is a curve that when you see the report of the correlation of your exponential regression, it's actually reporting the correlation of this transformed linear regression. So this is used by many software packages, this transformation idea, and it actually translates directly to plotting data on a semi-log paper and doing linear regression there. How about logarithmic regression? Well, that's just transforming the X data by taking a natural logarithm, then using linear regression on that transformed data. In other words, your new logarithmic X values with, I'll call U here, doing linear regression on the U, Y pairs, and then rewriting back in terms of natural log. So that's how the logarithmic regression is done on the TI-84 and the TI-Nspire. And yeah, I'll turn this back over to you, but I think it's just about time for us to.
Just about time for Mike, right? So one thing I just want to, this business about when do you have a good model and residuals, that is in the CED. That fits, comes along with polynomial regression, with trigonometric regression. So that residual idea is in all of the units, and it's something new. It's partly of the way of thinking of the College Board is that this course is not solely for pre-calculus preparation, but can serve as a good course for preparation for students who want to go in other directions. And so that's why they've included some of this modeling stuff in there, which I think is, coming from the statistics world, I think is really great. And so I just want to point out that there's a lot of resources for you in the pre-calculus. And I know I've noticed in the chat that you guys are sharing really good sources, but there's a lot of TI resources that are really nice. There's both for the 84 and for the Nspire. There's several different resources that are available for you to do. So take some time in your life and go investigate some of those and then share them with your others, whether you join the Facebook AP Calculus group or whatever, but sharing is what it's all about. All right, I'm turning it over to Mike.
All right, thank you so much. I know that I saw recently some chats go through about the Facebook community, so I just want to emphasize that again. It is a great place to get some of your questions asked and answered as well. As promised, we're giving away to one lucky winner a TI graphing calculator of their choice. And tonight's lucky winner is Victoria Rizzo. So Victoria, congratulations. Start thinking about which graphing calculator you would like to receive. I'll be reaching out to you very soon over email. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents for tonight. And if you're looking for the extra file, the TNS file for the TI-Nspire that Gail had mentioned, just hang tight. Take a look in your email in a couple days. You'll get a follow-up email from us that'll say, hey, thanks so much for attending. Here's a link to the recording so you can watch it at your own pace. Here's a link for the documents, which is going to be updated to include that new TI-Nspire document, and also a link for the certificate as well. So in case you're having any issues with any of these links tonight, again, you'll automatically get them in a follow-up email within a couple of days. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you have any questions for us, feel free to give us a call or reach out to us over email. We'd love to hear from you, ti-cares@ti.com or 1-800-TI-CARES over the phone. When you leave tonight, a brief survey will automatically appear in your browser. Again, this is the second, almost kind of third-ish AP Pre-Calc webinar we've done this fall, and we would love to hear your thoughts as to how we might be able to improve on future webinars. So if there's things that you haven't seen that you'd like to see, that'd be great to let us know. If there's things that we're doing well, those are also nice to hear as well. So please go ahead and share your thoughts in the post-webinar survey. Huge thanks to Gail and Tom for everything they put together for tonight. We really, really appreciate it.
Thanks to you guys.
Thank you.
Yep. Thanks everyone for joining us. We hope to see you back online next week. Have a great night.